So sometimes when we come to a study like this, it might be hard to understand what's actually going on. So this study specifically uses a one-way ANOVA to describe differences in academic achievement between two groups of middle schools. So this study, a comparative study of student achievement in traditional schools and schools of choice in North Carolina. So what we're going to do is we're going to go through this study and kind of break down and understand the one-way ANOVA to interpret it. So this study has some research questions, and we're going to focus on the first research question. So it says, are there significant differences in academic achievement scores of students in selected public middle schools of choice as measured by the end of grade test scores in reading? So we're going to look at reading scores specifically. We have two groups, and we're going to see if there's a significant difference between those two groups. So the authors have prepared this table to do descriptives and ANOVA for these reading scores. So here at the top, you can see the descriptive statistics. You can see that there are two groups of schools. There's choice schools. There's 24 schools in the choice group, and there's 24 groups in the traditional group. There's 24 schools in the traditional group. So you can see their mean score. This is for reading, remember, standard deviation, standard error, min, and max. So this is all great, but what we're going to do is we're going to focus specifically on this ANOVA table. So I'm not going to get into how we actually calculate the sum of squares, but we are going to talk about it. So here first we see between groups is the first row here, and then we have within groups, and then we have a total row here. You don't really need to deal with the total. So we're going to focus on these two rows first. So remember in ANOVA that our null hypothesis here, and we'll make this specific to this study, is that the average scores, we're going to use C for choice and then T for traditional. So the average reading scores of these two groups of schools are the same. That is our null hypothesis, and we're working to see if that is a true claim or not, or a claim that we can say or not. So this is our null hypothesis that we're working with, and this is the reason why we get this F statistic here and then a significance afterwards. So when we talk about between and within, yes, we are comparing means, but this is the analysis of variance. So imagine we have these two groups, and they have their own distribution of reading scores, right? So ANOVA asks if these two groups are far enough away that we can say that they have a significant difference. So this area here, this is the between groups understanding. And then the within groups is the error. That's the difference. That's how spread the distributions are for these two groups that we want to account for, because we have to account for that error to understand the difference between these two groups to see if they actually are significantly different. So we've got our between groups, and this is what we're really after. We want to make sure that this is big. We want to make sure that the difference between the groups is large, but within the groups, we want to make sure that that's as small as possible. So let's look here at the degrees of freedom to understand where they're coming from. So between groups, the degrees of freedom is 1. And basically what that is the groups minus 1. So the number of groups here is 2 because we've got choice and traditional. So that means 2 minus 1 is our degrees of freedom for between the groups. So within the groups, we've got a degrees of freedom of 46. Now, this is coming from here, the size of the groups. So the size of the groups are equal. So that's good. We don't have to do anything with that. So for within the groups, the equation is the number of groups times the group size minus 1. So we already said groups, number of groups is 2. And then from here, this is our sample size for within the groups. So we're going to do 24 minus 1 is equal to 2 times 23, which equals 46. And this is the degrees of freedom within. All right? So we've got 1 and 46. 1 and 46. All right, so to get this mean square, we are dividing the sum of squares by the degrees of freedom. So that's going to give us this mean square that's average for the within group's average error per observation. And then here, so we've got the sum of squares divided by the degrees of freedom to get us this mean square. Then we are dividing this between groups mean square by the within groups mean square. So it will be 1085.852 divided by 63.921 is going to equal the F score, which is 16.987. So 16.987 is actually big. So we really want this F to be large because we want the difference, we want the magnitude to be very large. We want this size difference that between, once we've accounted for this error within the groups, we want this to be quite large. So for this F to be 16.987, that's really good. That means that we have a large F statistics, which means that we are more likely to find significance. And here we do find significance. So this is the p-value, and it is significant at an alpha of 0.05 because this is smaller than this. So that means it's significant. So back to our null hypothesis. Our alternative hypothesis here is that the average for these two groups is not the same. We see a significant difference between these two average. And because this is a significant test, we reject the null. And we can conclude that there is a significant difference between these two groups. Now, because we are only comparing these two groups, this is the end of the analysis because we have that significant difference. Now, this does not tell us which one is greater than the other one or which one is smaller than the other one. We simply know that there is a significant difference between these two groups based on this ANOVA. So I hope that helps understand a little bit more about where these numbers come from and how we interpret it. But just remember, we always want a large F statistic because this is basically the magnitude between these two mean squares, and we want that to be large. We want this distance to be quite large once we've accounted for this error.